Sorry, I can't let you on. Hey, you didn't even measure me. What's the height requirement for this ride? Sorry, company policy, I can't tell you that. Is that Leo de Castro and Chris Peikert in one of their papers? Yep, but remember, we also represent all those brave souls who came before us. We can help you. Why don't you try formalizing your problem with some notation? Okay. The roller coaster guy has a function f, which is like the height requirements function. The function is supposed to take in my measurements x. And the output should be telling me whether or not I get into the ride. So we'll say that the output is some y, which is 0 or 1. The problem is I need the roller coaster guy to prove that f of x is equal to y without showing what f is. Yeah, how about applying f to x with a vector multiplication? Okay, what's a vector? Quick linear algebra review. A vector is a list of numbers. Here's a vector with k entries. We call it a column vector, and we say if it's real numbers, then we say it lives in zk. If we're dealing with integers, we might say it lives in zk, rkzk. We can also take its transpose to get a row vector. So here's a row vector of k entries. And finally, we can multiply two vectors. If we have a row vector and a column vector, we can simply multiply by doing this entry-wise multiplication and summing between the two vectors as such. Hey, isn't that the solution? All right, let me try this. So let's say my measurements, I represent it as bits, the 0, 1, 0, 1s. And let's say my function f, well, I guess let's just say the function f is checking if the first bit is there, is 1 or not. Then I could say f of x is equivalent to the vector multiplication between x and f. But hey, this function f doesn't actually do anything. It just checks if the first bit is 1 or not. That's not like the real function. How can we even do anything useful with this? Okay, we'll fix this later. Trust us. More importantly, f is not hidden. To verify this computation, I still need to know f. Oh, you know what? We can help you there. Here's an idea. What if we could somehow use the function to solve another problem? So instead of giving the function, I give the solution to another problem. So here's what I mean by that. Say if one knows that x transpose f equals y, then we have a solution to this other problem. We'll call that completeness. And let's say if we have a solution to the other problem, that should imply that x transpose f equals y. And we'll call that soundness. So with completeness and soundness, we know that if we give a solution to the other problem, it must absolutely be the case that x transpose f equals y. The roller coaster guy wants hiding. We don't want any information about f to be revealed. And finally, we don't want them to switch out what the function is. So we'll call that binding. Only the function f should be used here, no other function. So what is this problem? Well, before we explain it, quick linear algebra review. Matrix addition. A matrix is an array of numbers. So here's a matrix. It has m columns and n rows. And we'll say if we're doing with real entries, then it lives in R to the n by m. Or if we're dealing with integers z, we can do matrix vector multiplication. So here we have a matrix and a vector, and we can multiply them as such. And one way we can interpret this is we separate each row of C into its own row vector and then do these n-independent vector multiplications. And we can extend this to matrix multiplication by simply repeating the matrix vector multiplication for every column of Z. Well, let me tell you what the problem is. Given a matrix C bar and a vector U, I want you to find Z such that C bar Z is equal to U. And we'll call this pre-image sampling problem. But hey, I kind of recognize this. Normally we can solve this using regular linear algebra techniques. Yeah, that's true. So that's not the actual problem. Consider the set of all possible solutions Z that can satisfy that equation. It's more than just one. If C bar is wide enough, if we're working with real entries, it'll look like a plane that's been shifted away from the origin. If we're working over integers, then it will look like a bunch of discrete points, which we call a lattice, which it has been shifted away from the origin as well. And in particular, the harder version of the problem will be done with the integers. So suppose that all of our entries are working over the integers. Now the hard part is, imagine we impose a distribution over these points. So here's a Gaussian distribution. Gaussian is simply a distribution which points closer to the origin or have a higher density than the points away from the origin. And if you try to sample z, over this, what we call a discrete Gaussian, it is actually very difficult to do this efficiently when the matrix C bar and vector U are random. In other words, like when C bar is random, it is very hard to recover this nice shifted lattice structure. All right. But if this problem is so hard, how do we even solve it in the first place? Well, maybe you have something C bar that looks random, except it's actually structured secretly so that C bar T equals G. Hey, what's G? Quick linear algebra, Gadget edition. So here's the identity of size n. It's simply a bunch of ones along the diagonal and zeros everywhere else. It's an n by n matrix. And the key property is that the multiplication, it preserves any matrix or vector of the right dimension. Here's a cool thing you can do with matrices. It's called the Kronecker product. We'll call it the tensor product henceforth. Suppose you have two matrices A, tensor B. For every entry of A, you take that entry and you replace it with B scaled by that entry. And so in a way, this multiplies the dimensions of A and B together. It preserves the information of both A and B in one product. Let's define the Gadget vector. So the Gadget vector is a powers of 2 vector, column vector. It has a key property where if we take the vector product with a binary decomposition of some integer, then you can check and see that the output will just be the original integer that we put in, u. And this is nice. You can do more than just, one of these vectors. We can form what's called a Gadget matrix, where we take the identity and we tensor it by G transpose. And so what that looks like is it looks like the identity with a bunch of powers of 2. The nice property is if you take a matrix A of the right dimensions and you take its binary decomposition, that is, we replace every entry of A with a column vector of the binary representation of that entry, then G times the binary decomposition of A will get you A back, just like the Gadget vector, but for matrices. And so now we're talking about what if C bar looks random, but is actually structured in such a way where we know a matrix T called the trapdoor, where C bar T is equal to the Gadget matrix. And the Gadget matrix is very well structured. So well structured that you can efficiently pre-image sample G. So you can sample this integer vector Z prime from the discrete Gaussian very well. And using Z prime, we can get a vector Z, which is just G times Z prime, sampled from the discrete Gaussian as a solution for the original pre-image sampling problem. So how can we efficiently pre-image sample the Gadget matrix? First, we should observe that this bit decomposition property of the Gadget matrix means that with just zeros and ones, you can recover any vector, any matrix out of G. So this means that G is like a function that has a very good amount of diffusion. And so if you have Z with even small bounded entries, you'll get a wide amount of outputs. And so we can use that idea. Say that we, sample a bunch of points Z uniformly with small entries. And let's say we accept Z with the probability described by the discrete Gaussian. So this is known as rejection sampling. And this lets us get a bunch of samples that look like they're from the discrete Gaussian. Now, the only thing is we haven't isolated the set of Z's which satisfy GZ equals U. So now the only thing we have to do is isolate the solutions Z which satisfy GZ equals U and pick one uniformly at random, then we would have picked pre-image sample to Z which satisfies GZ equals U from the discrete Gaussian. Bang! So if we have randomish C bar and U, it's hard to sample Z from the discrete Gaussian unless you know C bar T equals G. But like, how does it actually help me? So if we want the problem we're relating to be this pre-image sampling problem, then we want it to satisfy these 4 properties. If we know what the function evaluates to, then we should pre-image sample a Z. If we have a solution Z, then we should know what the function F evaluates to. That's completeness and soundness. And furthermore, when we reveal this solution Z, we want to make sure that it hides F. And lastly, we want to make sure that only the function F is used. Hey, wait, I observed something. Wait. If C bar has a trapdoor, then we have an efficient way to pre-image sample Z. So wouldn't it be better to just replace that in completeness? Precisely. Hey, and why don't you try to work it out? How can you actually make something that satisfies these 4 properties? Okay. Let's start with completeness. We'll start with x transpose F equals Y. And I eventually want to get something involving G. So why don't I move Y to the left side and add G? And then I wanted something that looks like C bar times T equals G. Why don't I try something like this? This seems to work. You know, I get x transpose F minus Y plus G equals G, which should be true. Whoa, slow down there, buddy. You gotta check your dimensions. That X and Y, they both have a height of 1, but G is this like humongously tall matrix of height n, and you're not even looking at this F and I. We don't even know how to work with these dimensions. Why don't I help you out? Try this. Oh, hey, pretty nifty. And why don't I simplify this down a little bit? Bam, completeness, done. What's next? Soundness? Okay, another way to look at soundness is like, if x transpose F is not equal to Y, can I still efficiently pre-image sample Z? The way we know how to efficiently pre-image sample is if we know a trapdoor exists. So let's try this out. Let's say we have 2 different values for the function and the supposed output. What happens when I plug this into my matrix? I have C bar and T, and this is what the output looks like. And oh no, I get 2G, and this is still a useful trapdoor. How can I make it so there's no trapdoor when x transpose F is not equal to Y? There's something weird happening with x transpose F and Y. Because we're working with Boolean functions, when they're equal to each other, they're either 0 or 2, but when they're not, they sum to 1. Okay, well, what if I shift it so that shift everything by 1? Then when x transpose F is equal to Y, we'll get plus or minus 1, but when they're not, we get 0. And like 0, maybe it's useful. Let's see what happens. So let's plug this in. Let's change the C bar a little bit. So now the output is this x transpose F plus Y minus 1. Yeah, and so when x transpose F equals Y, that's a useful trapdoor. We get plus or minus G. But when they're not equal, we get 0, and that's useless because you can't do anything with 0. So we have soundness. Hey, you did prove if x transpose F is not equal to Y that you can't generate a trapdoor easily. But don't forget that we need C bar and U to be random. If C bar is not random, it might be easy to pre-image sample Z even without this trapdoor T. Okay, let's see what's going on. So this is my equation. How do I make it more random? How about I just stick a random matrix in the front? Here, I'll just add a random matrix C. Oh wait, then my output would change. We would get CF tensor I. Maybe I can remove that by adjusting the second half of the matrix. Here, I'll stick in a CF. It'll be the negation of this extra part. And everything should be fine, right? So I have something that kind of looks random. Only the first half I injected this random matrix C. Does this really stop us from efficiently pre-image sampling without trapdoor? Yeah, it's random enough. Congratulations, you have soundness. Yay. Okay, how about hiding? Let's see. So hiding, I just have to see if checking the solution will reveal something about the function f. I know z will be sampled from the discrete Gaussian, so that doesn't show anything about f, and u is just some random integer. Let's check c bar though. So what do I have to do to actually construct c bar? Let's see, c is good, c is just random, x is the input, y is the output. And I think it's okay to know y, but what about cf? Cf is negative c times f tensor I. Wait a second, there's f in here. Uh-oh. So why did I even have cf set up like this? I need to apply the function somehow. So I have my input tensored with g, and then to apply f, I need that. And so that's where I get f tensor I. But is this the only way I can apply the function? Hey, remember the properties of G? Oh yeah, I remember. It's if you have a matrix A, then the bit decomposition multiplied by G, you'll get A back. Let's see if we can apply it to our function. So let's say we have our input on the left. If we take the binary decomposition of f tensor G, it looks like we still get the output. And hey, wait. Can we not do the same thing as we did before? Can we do something similar where we like pre-image sample this f tensor G so that we get the desired output? Yeah. Let's call that special pre-image sampling G inverse. It still samples from the discrete Gaussian. Okay, so now our verification equation looks like this, where CF is negative C G inverse of f tensor G. And because we did this pre-image sampling, we get a vector that is sampled from the discrete Gaussian, and that now hides f. Yay! Okay, we get hiding down. Here's for the last one, binding. Only f can be used. But hiding told us that we are not supposed to know anything about f. So how can we even verify if we're still using the exact same function if we know nothing about the original function? Like imagine we had a approximate function f prime which almost works exactly like f, except maybe on one input. Like, how would we tell the difference between those two functions? Leo, Chris, I don't know what to do. Okay, you know what? You're right. We don't really know anything about f, so we will have to trust that f is being used correctly. But instead of binding on the function f, maybe we should bind on the output. We want it to be hard to be able to produce two solutions, z and z prime, which have different outputs, y and y prime. But when is it hard to do something? Like, how would I prove that something is hard to do? Well, there's two ways of going about it. One is that you prove there's no efficient algorithm to solve a problem. And more likely, number two is you show that by doing this hard thing, you solve another problem that is known to be hard. Okay, let's break binding. Let's say I have two different solutions, z and z prime, and they have two different outputs, y and y prime. If I have soundness, I know there's trapdoors for each of the c bar and c bar primes. And why don't I unravel this a little further? I'll just do the multiplications out, and so now we have these two different equations. I can subtract them. And on the right-hand side, I know that y minus y prime must be plus or minus 1 because my outputs must be binary. So I know the right-hand side is plus or minus g. And why don't I apply a property of the Gadget matrix, take the bit decomposition of 1, 0, 0, 0, 0, and if I multiply that on both sides, then I'll get plus or minus 1, 0, 0, 0 on the right-hand side. Hey, nice, this looks like SIS. What's SIS? Quick lineage review, short edition. The short integer solutions problem is as follows. Given a random matrix A, find vectors x and e with small integer entries such that ax equals e. And one way you can think about this is take the columns of A as vectors, so A1, A2, A, and so on. And since x has small entries, find small linear combinations of those such that the result is small, since E must have small entries too. And the important thing about SIS, for security is that we think it's hard to solve SAS with the right parameters if some other lattice problems are hard in the worst case. And these problems can be, we think, are very hard. Keyword is that they are believed to be post-quantum secure. Okay, so let's check if this really solves SAS. C plus X transpose tensored with G looks random, just like A. And on the right-hand side, we have a vector that does have very small coefficients. Okay, and now let's check the inside. So we have a lot of pre-image sampling from the discrete Gaussian. So we know those entries have to be relatively small. The discrete Gaussian has highest mass near the origin. Similarly, the difference between two of these vectors must also be small, and their multiplications have to also be small. At the end of the day, we get a small vector. Okay, cool. Yay! Breaking binding solved SIS, which means that we get binding. So, did we do it? Did we really evaluate f without revealing the function? Yes, we did. And you've actually made a functional commitment scheme. It's just 4 algorithms. And here's how they work. Suppose there's some trusted third-party or random oracle. They have a setup algorithm which produces public parameters for everyone. The prover has a function called commit that takes in the public parameters and a function f. And they produce a commitment to the function f. Later, at a later point in time, the prover has an opening function which takes in the public parameters f and x and produces some auxiliary information which should hopefully attest to what the evaluation of f on x is. And lastly, the verifier has a verify algorithm which takes in the public parameters, the commitment to f, the input x, and the candidate value y, as well as the what's called the opening or proof pi fx, and checks if f of x really is equal to y or not. For this particular problem, we're interested in 4 properties. Correctness, which means that if the prover and verifier are working, then they really will be able to verify if f of x equals y. Function hiding, the commitment to f should not reveal anything about f. Zero knowledge evaluations, the openings pi fx should reveal nothing about f. And lastly, evaluation binding. If we fix the public parameters, the commitment, the input x, then it should be hard to verify 2 different outputs because the commitment should really commit to one function. You know, I see it now. The prover is the roller coaster and the verifier is me. Correctness is kind of saying that the prover can prove that I am or am not admitted. Function hiding and zero knowledge evaluations means that I'm not able to know what the exact height requirements are. And finally, evaluation binding means that the prover can't change their mind about whether I'm admitted or denied. Like they have to commit to one decision from the beginning. So the result is really just a fixed function of my measurements x. Cool. So can you construct this functional commitment scheme? Okay, so what was I thinking about? Right, this was the verification equation. Let's say setup generates the random matrix C and vector U. We'll say the commitment produced is CF, which is, like the function kind of being applied to C. Let's make the opening the solution Z to the pre-image sampling problem. Finally, verify can just check whether the solution Z solves the pre-image sampling problem. Ding, ding, ding. Let's update that scoreboard. Do we have correctness? Yeah, it follows from completeness. Function hiding and zero knowledge evaluations. Well, that follows from hiding. Evaluation binding follows from soundness and binding. It seems like f is pretty restricted. It has to be these Boolean linear functions. So basically only checking if one bit happens at a time. Can we do more than just linear functions? Yeah, we can. Here's how we can get all functions. So think of every function as a network of additions and multiplications. So if we have an input x with a bunch of bits, x1 through xk, then we can do a bunch of multiplications or additions to eventually get the output f of x. And so long as we can compose these additions and multiplications, we can get any function. So like for this scheme, we can say we have two functions, f1 represented by f1 and f2, then we can apply them one after another, resulting in one final commitment C f2 composed with f1, and output f2 of f1x. And here's the construction. So for addition, we got this, and for multiplication, we got this. Geez, thank you a lot. Wow, this is I know exactly what to do now.